You know, the world isn't really black and white, is it? It's full of maybes, what ifs, all those shades of gray. So how in the world do we get computers to reason about that? Today we're diving into two really powerful ways to tackle that problem head on.
So here's the plan. We'll start with why old-school true or false logic just doesn't cut it anymore. Then we'll look at the common ancestor for both of the systems we're talking about today. After that, we're going to go down two different paths. One that's all about pure hard probability, and another that's more about, well, fuzzy logic. And stick around, because at the end, we're going to see why you can't just pick one. You really need both.
All right, let's kick things off. Section 1. Logic for an uncertain world. Time to move beyond black and white.
Okay, picture this, a self-driving car. You don't just ask if it's working or not working. No way. You have to ask things like, what's the chance it'll see and stop for a person crossing the street in the pouring rain? Or think about a financial model. What's the probability of a market crash if X, Y, and Z happen? See, these are not simple yes or no questions.
And that really gets to the heart of the problem. Traditional logic, Boolean logic, is basically a light switch. It's either on or off, true or false, 1 or 0. And that's just not how the real world works, right? It can't handle stuff like noisy sensor data, or different levels of confidence, or the actual chance of something happening. We need something way more sophisticated.
So where do we start? Well, it turns out both of these advanced logics we're going to look at have a common ancestor, a powerful foundation, and that brings us to Section 2, the Mu Calculus.
So this thing is called the Modal Mu Calculus, and what makes it so special is how good it is at describing systems that change over time. Its secret weapon is something called fixed-point operators. And yeah, I know, that sounds super technical. Don't worry about the name. All you need to know is they let you ask really important questions about systems that run forever, like an operating system. Questions like, is it guaranteed that this good thing will eventually happen? Or can we be sure this really bad thing will never happen? It's a perfect base to build on.
So from this one powerful foundation, the road splits. We get two different upgrades for dealing with uncertainty. Down one path, you've got the Probabilistic Mu Calculus, which, as the name suggests, is all about pure probability. And down the other, you've got the Lucasiewicz Mu Calculus. Yeah, it's a mouthful. This one is all about fuzzy logic. So let's take that first path and see where it leads.
All right, Section 3. We're on Path 1, pure probability. We're talking about the Probabilistic Mu Calculus. This whole approach is about getting super precise and putting a hard number on every single uncertainty.
So this logic works on systems that you can basically draw out like a flowchart. Think of it as a map of every possible state your system could be in. But here's the cool part. The lines connecting the states aren't just arrows. They have numbers on them, exact probabilities. So it's not just you might go to state A or state B. There is a precise 70% chance you go to state A and a 30% chance you go to state B. Everything is governed by the mathematical roll of a dice.
So how does it actually do this? Well, it takes that base mu calculus we talked about and bolts on some new tools just for probability. The big change is that when you ask it a question about the system, it doesn't spit out a simple true or false. Instead, it gives you a number for every state, a value between 0 and 1, and that number means something very specific. It's the exact probability that what you're asking about is true, right from that starting point.
Okay, but it wasn't perfect, at least not at first. The early versions had a pretty big blind spot. There's another really important logic out there called PCTL. It's kind of the gold standard for checking probabilistic systems, and this new logic, well, it couldn't quite speak the same language. It just wasn't expressive enough. It was like having a fantastic toolkit, but you're missing the one wrench you need for the job. It was clear it needed an upgrade.
And this is how science works, right? The challenge was clear. Make it compatible with PCTL. The solution? Researchers added new operators, new mathematical gadgets to the logic. And what came out the other side was a much more powerful version. They call it a tractable version, which basically means that even though the problems it solves are incredibly complex, we can actually get a computer to figure them out in a reasonable amount of time. It could finally do the job it was meant to do.
Okay, let's hit rewind and go back to that fork in the road. It's time to check out the other path. Section 4 is all about fuzzy logic, and our friend the Lucasiewicz Mu Calculus. This approach looks at uncertainty in a totally different way. It's not about pure probability. It's about something called fuzzy logic.
So this logic, let's just call it Lu, it's easier. It works on a different kind of system model.
a model that has both probability and something called non-determinism. And this is a really important distinction. See, a probabilistic choice is like rolling a die. You know the exact odds. Non-determinism is when you have a choice but you have no idea what the odds are. Think about a person using your app. Are they going to click button A or button B? You can't assign a probability to that. That's a non-deterministic choice, and this logic is built to handle both kinds of uncertainty.
The whole philosophy here is just different. It's based on this fuzzy logic. So instead of a single and a single or, you get weak and strong versions of them. And remember that 0 to 1 value? Here, it doesn't mean probability. It means a degree of truth. So think about a statement like, the room is warm. That's not true or false, right? It can be kind of true. That's the idea here. It's about how much we believe a statement, not the statistical chance of it happening. And here's the kicker. Remember how the first logic we looked at needed a whole upgrade just to be able to handle PCTL? Well, this fuzzy logic, it could do it from day one, right out of the box. Its fundamental design was just naturally powerful enough to express all those complex ideas from the get-go.
So there you have it, two really powerful logics, but with totally different ways of looking at the world. So that brings us to the final showdown, Section 5, why we need both. Let's put them head-to-head and see what they're each good at. Okay, this chart really sums it up nicely. On one side, you've got the probabilistic calculus. Its core idea is, well, pure probability. Its values are real numbers representing a chance of something happening, and it's perfect for modeling systems where you know the odds, like a network protocol. On the other side, you've got the Lucasiewicz calculus. Its whole deal is many-valued, fuzzy logic. Its values represent a degree of truth, not a probability. It's built for systems that have both randomness and that unpredictable non-determinism. And as we saw, it was powerful enough to encode PCTL right from the start. So who wins? What's the final verdict? Well, the truth is, there isn't a single winner. It's all about picking the right tool for the job. If your problem is all about clean, known probabilities, like analyzing a network that drops packets at a certain rate, then the probabilistic Mu calculus is your guy. But if you're dealing with messy, real-world stuff like ambiguous sensor readings or vague human concepts like safe or fast, then the fuzzy logic approach is going to be way more useful. But what does it actually take to use these in the real world? Is it easy? Not exactly. The math behind model checking can get really intense. For the probabilistic logic, the problem is known to be very hard. Think of a ridiculously hard Sudoku puzzle. Finding the solution is a nightmare. It could take you forever. But if someone just hands you a completed puzzle, checking if it's correct is pretty straightforward. That's kind of what we're dealing with here. It's a tough nut to crack, but it's not impossible, and computer scientists have found clever ways to tackle it.
So why should you care about any of this? Because this isn't just some abstract theory anymore. Being able to prove things about systems that live in an uncertain world, that is absolutely critical. It's the foundation for building trustworthy tech, the stuff we're all going to rely on in the future.
And that leaves me with one final question for you to chew on. As AI gets smarter and our systems get more complex, which of these approaches do you think is going to be more important? Will we need the cold, hard certainty of pure probability? Or will we need a logic that's a little more human and fuzzy? The future of trustworthy AI might just depend on the answer.